Gentlemen, let's broaden our minds.
Hey, welcome to our video on how to count atoms. Now, why is this an important concept to learn? Well, in chemistry, it's very important to be able to count atoms because if we're wanting to calculate the mass of atoms or molecules, we need to know how many there are. So if we start off by looking at our first example of a water molecule, let's see if we can find out how many of each of these atoms there are in one molecule of water. So we'll start off with hydrogen. How many hydrogens do you think are in this one water molecule here? If you said 2, you would have been correct. What about for oxygen? So we look over here. If you said 1, you would be correct. This 2 here is called a subscript. So subscripts indicate how many atoms of a particular element are in a molecule. So our subscripts are these numbers here, okay, that are smaller, and they're generally after the letter representing the atom. So we have 2 hydrogens, and over here we have 1 oxygen. It's not necessary to write the 1, so just know if there's no number, no subscript number after that atom, that it is 1. Now, what about this molecule? How many hydrogens do you think are in this molecule of water? What about oxygen? Did you say 6 hydrogen and 3 oxygen? How did I come up with that? Well, it all has to do with coefficients. So the coefficients are the big numbers in front of the molecule. And this indicates the number of molecules that we have. So we have 3 water molecules. So if we look at a visual here, these are 3 molecules of water. If we count them up, we have 1, 2, 3 oxygens, 1, 2, 3, 4, 5, 6 hydrogens, which is exactly what we had here. So generally what we're going to do is multiply the coefficient by the subscripts, and that'll give us how many of each atom we have. So 3 times 2 gives us 6 hydrogens. 3 times 1 gives us 3 oxygens. So let's go ahead and practice with a couple of problems here. So I have for you ethanol, just C2H5OH, which is an alcohol, which has the OH at the end, which indicates that it is an alcohol, as we discussed in class 4. So let's try and figure out, to start off, how many carbons there are. So 6 times 2 carbons should give us 12. What about hydrogen? How many hydrogen do you think there are? Did you say 36? If not, I bet you forgot about this H at the end. 6, and then we have 5 here, and an additional 1 here. So 6 times 6 gives you 36. What about for oxygen? Did you say 6? If so, great. 6 times 1 will give you 6. Let's try another. So in this example, we have glucose, C6H12O6. Hopefully you remember that from 7th grade from respiration and photosynthesis. So how many carbons do we have in this molecule? Hopefully you said 24. 6 times 4 is 24. What about for hydrogen? Did you get 48? 12 times 4, 48. And lastly, for oxygen, hopefully you've got 24. 4 times 6, 24.
So let's get started. We're going to start, the first one we're going to talk about is the combustion of hydrogen. This is the Hindenburg explosion, and after this we quit putting hydrogen gas into blimps for obvious reasons. But essentially what happens is hydrogen combines with oxygen. Okay, so if we look at the equation down here at the bottom, the equation as it is H2 plus O2 yields water, or H2O, and we're going to get a lot of energy out of there as well. Now, the first thing we need to talk about is what these numbers actually mean. So this 2 down here is a subscript, and that means that it tells you how many atoms of hydrogen are in a molecule. And so this is what the molecule of hydrogen would look like. We're going to have 2 atoms of hydrogen. The thing that you need to remember is that you can never change the subscripts. Subscripts have to remain the same, because if you change it, you're changing what that molecule actually is. And so this would be H2, this would be O2, so we have 2 oxygen molecules attached together. Then finally we have H2O, and H2O is 1 oxygen and 2 hydrogens on either side. And so when I look at this, a lot of people will just try to go and answer this, but maybe we need to step back a little bit and actually look graphically at what's going on here. And so when I look at this, I can see here's reactants before the reaction and products. And so just looking at it, when these are graphically shown, you can see that I have 2 of these red oxygen atoms on the left side and only 1 on the right. And so the first thing you might want to do is kind of double that. And so let me do that. Okay, so now visually we've got 2 water molecules, and so I've got 2 reds on the right side and 2 reds on the left side. You'll also notice, so that's balanced, that the hydrogens are changed. And so I have 4 hydrogens on the right side, but I only have 2 on the left side. So now let me click it again, and we've got a balanced equation. In other words, I can never change the subscripts. I can never change what these molecules are. But when you're balancing equations, what you're trying to do is add more of the molecules so you can see that reactants and products will be balanced. Okay, now how do we actually write that out? So we can put in front of here what are called coefficients. And coefficients are numbers in front of the molecule. It tells you how many there are. And so there is 1 oxygen, and we never write the coefficient of 1. And so you don't want to write 1 as a coefficient. If it's a coefficient of 1, you just leave it blank. But let's go over here to H2. You've got this H2, that H2, and so you have 2H2. So that would be on the left side. If we go on to the right side, you have this molecule of water, this molecule of water, and so we have 2 molecules of water on the right side. And so if we step through this, this means we have 2 molecules of H2, so that would be 4 hydrogens on the left side. After you balance an equation, you want to go back and look at it and make sure it's balanced. Over here we have 2 H2s as well, so we have 4 hydrogens. We have 2 oxygens on the left side, and we have 2, this coefficient multiplies times this whole thing, so we have 2 oxygens on the right side as well. And so we would call that a balanced equation. And so hopefully just by looking at it graphically, that might help a little bit. Let's go to the next one. Next one in a chemistry lab is, you see it all the time. This is a Bunsen burner, and these are some flames from a Bunsen burner. And so a Bunsen burner works using a gas called methane, and methane is CH4. So if we take a look at methane, methane looks like this right here. It's got 1 carbon molecule, and then it's got 4 hydrogens attached around the outside. And when we burn methane, what that really means is that we're combining methane with oxygen, and we're creating these 2 things in complete combustion. We're creating some carbon dioxide gas, that's 1 carbon, 2 oxygens, and then we're creating a little bit of water. The other thing we produce is going to be energy. Okay, so if you look at this just graphically on the left side and on the right side, the first thing, at least to me, that jumps out is that there's way more hydrogen on the left side than the right side. So the first thing I could do would be to add another water on the right side. So if I've added another water on the right side, the yellow balls on the right now match the yellow balls on the left. The carbon, there's only 1 on the left, matches the 1 on the right, and so we must be getting really close. But I've got 4 reds on the right, and I only have 2. And so I have to add that as a whole molecule. So if I add one more molecule of oxygen, now we have a balanced equation. So how do we write that out? So methane on the left side, I have one methane, but I'm not going to write the number 1. How many molecules of oxygen do we have? We have 2. And so I'm going to put a 2 as a coefficient right here. Now on the right side, we only have one carbon dioxide, so I'm not going to put a 1, but there should be, in your mind, a 1 there. And then how much water do we have? We have just 2 waters. And so I'm going to put 2 right here. Now we could go through the whole thing. So how many carbons do we have? 1 on the left, 1 on the right. How many hydrogen do we have? 4 on the left. And this 2 is multiplied the subscript. So we've got 4 on the right and 4 on the left. And then if we look at oxygen, we've got 4 on the left. And then we've got 2 oxygen here, and we have 2 oxygen there. And so when I'm solving and trying to balance equations, I'm not really seeing these, but if that helps you visualize it, then it'll help you do better at that. So let's try it. So the only way to get better at this is to just practice. And so let's try a few, and I'll show you how I would think through this in my mind. Let's go to the next one. On the left side, we've got sodium, we've got chlorine gas, and then we're making table salt. And so if you want to write this out, you could. We've got Na, and I've got 1 of those. I've got chlorine on the left side, and I've got 2 of those. So that's on the left side. That's on the reactant side. Now let's go to the product side. How many sodium do we have? We only have 1 sodium. And how many chlorine do we have on the right side? Well, we only have 1 chlorine. So that's a problem, because on the product side, we only have 1 atom of chlorine. And on the reactant side, we actually have 2. So how could I fix that? Well, let's try to go back. Let's say I've got too few chlorine on this side. So let me just try and add the next step, which is to add a 2 on the right side. So by adding a 2 on the right side, I've taken care of my chlorine. So on the right side now, I have 2 sodium and 2 chlorine. But I've set up with another problem. In other words, I have 2 sodium on the right side, so now I have to balance that over here. So I'm going to come back here and write a 2 over here, which that makes this a 2. Okay, so now we've got 2, 2, 2, 2, and that's balanced. And so the right answer for that one is to put a 2 in front of the sodium and then a 2 in front of the sodium chloride. And that's a balanced equation. Remember, you can never change the subscript. All right, let's do another one. Another one, and so these are getting progressively harder, and so I'll give you some tips as far as that goes. The first tip would be this. If we look at this one, we've got silver sulfide, silver, and then sulfur. And so this 8 jumps out right away. So on the right side, I've got 8 sulfur atoms. If we look on the left side, I've only got 1. And so as a bare minimum, I'm going to try writing an 8 right here. Let's see what that does. Well, now we have 8 sulfur on the left side, 8 sulfur on the right side. But our silvers aren't matching. So on the left side, we actually have 16 silver, but on the right side, we only have 1. And so let me just try writing a 16 down. So now that's a balanced equation. So we could go through 16 silver, 8 sulfur, and that's going to be a balanced equation. The nice thing about balancing equations is you can always check it at the end, and you know that you are right. It's not like you're maybe right. You absolutely are right as long as you're just adding the coefficients.
Where does all this stuff come from? This rock, that cow, your heart. Not the things themselves, mind you, but what they're made of, the atoms that are the fabric of all things. To answer that question, we look to the law of conservation of mass. This law says, take an isolated system, defined by a boundary that matter and energy cannot cross. Inside this system, mass, aka matter and energy, can neither be created nor destroyed. The universe, to the best of our knowledge, is an isolated system. But before we get to that, let's look at a much smaller and simpler one. Here we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. With a little energy, our molecules can really get moving. These atoms can bond together to form familiar molecules. Here's water, and here's carbon dioxide. We can't create or destroy mass. We're stuck with what we've got. So what can we do? They have a mind of their own. Let's see. They've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar and some oxygen gas. Our atoms are all accounted for, 6 carbon, 12 hydrogen, and 18 oxygen. The energy we applied is now stored in the bonds between atoms. We can re-release that energy by breaking that sugar back into water and carbon dioxide, and still, same atoms. Let's put a few of our atoms aside and try something a little more explosive. This here is methane, most commonly associated with cow flatulence, but also used for rocket fuel. If we add some oxygen and a little bit of energy, like you might get from a lit match, it combusts into carbon dioxide, water, and even more energy. Notice, our methane started with 4 hydrogen, and at the end, we still have 4 hydrogen, captured in 2 water molecules. For a grand finale, here's propane, another combustible gas. We add oxygen, light it up, and boom, more water and carbon dioxide. This time we get 3 CO2s, because the propane molecule started with 3 carbon atoms, and they have nowhere else to go. There are many other reactions we can model with this small set of atoms, and the law of conservation of mass always holds true. Whatever matter and energy go into a chemical reaction are present and accounted for when it's complete. So if mass can't be created or destroyed, where did these atoms come from in the first place? Let's turn back the clock and see. Further, 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 too far. Okay, there it is. The Big Bang. Our hydrogen formed from a high-energy soup of particles in the 3 minutes that followed the birth of our universe. Eventually, clusters of atoms accumulated and formed stars. Within these stars, nuclear reactions fused light elements, such as hydrogen and helium, to form heavier elements, such as carbon and oxygen. At first glance, these reactions may look like they're breaking the law, because they release an astounding amount of energy, seemingly out of nowhere. However, thanks to Einstein's famous equation, we know that energy is equivalent to mass. It turns out that the total mass of the starting atoms is very slightly more than the mass of the products, and that loss of mass perfectly corresponds to the gain in energy, which radiates out from the star as light, heat, and energetic particles. Eventually, this star went supernova and scattered its elements across space. Long story short, they found each other and atoms from other supernovas, formed the Earth, and 4.6 billion years later, got scooped up to play their parts in our little isolated system. But they're not nearly as interesting as the atoms that came together to form you, or that cow, or this rock. And that is why, as Carl Sagan famously told us, we are all made of star stuff.